Welcome back to Mechanical Engineering Made Simple.
It is great to be back.
Today, we are walking into a situation that I think every single one of you out there has faced in some form or another.
Oh, absolutely.
We have a bit of a mystery on our hands. It's a tech thriller, honestly.
Right.
But instead of international espionage and, spies and microfilms, it is set inside the high-stakes, high-stress, caffeine-fueled world of a thermal testing lab.
A narrative involving one of the most notoriously misunderstood concepts in the entire engineering canon.
Right.
We are talking about the ghost in the machine.
Exactly. So before we get into the heavy theory, I really want to set the scene for everyone listening.
Paint the picture.
I want you to picture a specific professional. Let us just call him the engineer.
The engineer. Okay.
And he isn't a rookie. He is smart. He is capable. He has, 10 or maybe 15 years of experience under his belt. He has seen it all.
Right. He's the guy you call when the simulation just refuses to match reality.
Exactly. He knows his way around a PID controller, a soldering iron, and he probably knows the specific smell of burning capacitors by heart.
Oh, we all know that smell.
We do. And right now, the engineer is running a critical validation test on a brand new, high-efficiency engine prototype.
High stakes?
The stakes are massive. This is not just a minor tweak. This engine is supposed to be the next big leap in thermal efficiency.
So we are talking about shaving percentages off fuel consumption that could mean millions of dollars.
Millions. So it is high pressure, high temperatures, and extremely high expectations from management.
Who are probably pacing outside the glass window of the test cell right now.
Oh, without a doubt. The trifecta of engineering stress.
Yeah.
So the engineer sets up his test rig.
Meticulously, I assume.
Very meticulously.
Yeah.
He has got Type K thermocouples plastered all over the exhaust manifold. He has high-sensitivity pressure sensors monitoring the flow across a porous ceramic particulate filter.
Okay, standard setup.
He double-checks the wiring, he checks the grounds, flips the switch, and the engine roars to life.
The floor vibrates.
The smell of hot metal fills the air. And he sits back, grabs his coffee, and looks at the data acquisition screen.
And that inevitably is when the trouble starts.
The numbers are lying to him.
Or at least they don't make any sense based on what he learned in his standard thermodynamics class.
Right. The temperature readings are drifting, even though the engine block thermal mass should be totally stable by now.
It is fluctuating in a way that suggests the engine is breathing, but the RPM is totally constant.
Yes. And weirder still, his pressure sensors on that filter are showing a gradient, a distinct pressure difference.
Even when the gas flow is completely shut off.
Even when the flow is zero.
He is seeing ghosts.
He really is. He is seeing pressure where there should be equilibrium. He is seeing heat fluctuations where there should be steady numbers.
Oh, he starts sweating.
He checks the sensors. They seem fine. He checks the DAQ board. It is fine. He starts wondering if the prototype itself is failing. Like, is a seal broken? Is combustion completely unstable?
The engineer is panicking because he thinks the machine is breaking,
But
the machine is not breaking. The engine is likely perfectly fine. What is failing him is his understanding of the physics of measurement.
because he was falling into a trap.
He is falling into the trap of thermostatics.
Thermostatics. Okay, break that down.
Well, he is trying to apply the comfortable, simple rules of classical equilibrium to a system that is very much alive with flow.
Right.
He is operating in the wild, untamed world of irreversible thermodynamics.
That name always sounds so ominous to me. Irreversible thermodynamics. It sounds like a mistake you cannot undo, like accidentally deleting the entire production database.
In a way, it really is about things that cannot be undone. It is the study of systems that are not settled.
Okay.
Classical thermodynamics, the stuff we all learn in Thermo 101, is mostly about states of rest. You have a box of gas, you wait a million years, what does it look like? That is equilibrium.
Right, everything has stopped moving.
Exactly. But the engineer isn't dealing with a box of gas at rest. He is dealing with a roaring engine.
He is dealing with systems where heat, electricity, and matter are all moving simultaneously.
And more importantly, and this is the key to this entire deep dive, they are interfering with each other.
They are crossing lanes.
Yes. To solve the engineer's problem and to fix his data so he doesn't scrap a perfectly good engine, we really have to look at what happens when these fundamental forces collide.
And to guide us through this ghostly terrain, we are diving deep into some source material, specifically covering irreversible thermodynamics,
We are going to focus on the heavy hitters today,
entropy production,
on Sager's reciprocal relations.
and the hidden complexities of thermoelectricity.
We're going to troubleshoot the engineer's rig step by step, using the text to explain exactly why his sensors are acting haunted.
So let us go to the scene of the crime, part 1, the setup and the steady-state fallacy.
Okay, set it up.
The engineer is looking at a specific component. Let's say it is a metal support bar connecting the hot engine block to the cooler mounting frame.
Got it.
He looks at his thermal camera, sees the gradient is completely stable, and he thinks to himself, okay, the temperatures are constant at my sensor points, so the system is in equilibrium.
And that is his first fundamental mistake.
Why?
He is confusing steady state with equilibrium.
I feel like we use those terms interchangeably in casual conversation all the time, though. Like, oh, things have settled down, we're in equilibrium.
We do, but it is a massive difference in physics.
What is the actual rigorous difference?
In classical thermodynamics, which, again, we should probably call thermostatics, equilibrium essentially means death.
Death.
Thermally speaking, yes, it means everything is totally uniform. If that bar were truly in equilibrium, the temperature would be exactly the same at the engine end, the middle, and the frame end.
There would be no flow of heat.
Zero. No energy moving. It would be dead. The entropy would be absolutely maximized, and nothing interesting would ever happen again.
But in this case, one end of the bar is bolted to a combustion engine running at hundreds of degrees.
And the other is bolted to a cold frame in an air-conditioned room.
So you have a massive potential difference.
Exactly. Heat is pouring into the hot end and draining out of the cold end.
Okay, so it is flowing.
Right. Now, if the rate of heat entering exactly equals the rate of heat leaving, the temperature at any specific physical point, say exactly 2 inches from the engine block, will not change over time.
It stays at, say, 150 degrees permanently.
Yes. That is a steady state.
So the variables are constant in time.
But they vary in position, and importantly, there is a flux. There is a flow. It is dynamic stability, not static stability.
So to the engineer, looking at a single thermometer value, it looks calm. It looks like a still pond.
But underneath, there's a rushing river of energy.
Precisely. And that river implies something profound about entropy. This is where the source material gets really interesting, and where the engineer's intuition usually fails him.
Well, I think most people, myself included back in the day, assume that if the temperature isn't changing, the entropy of the system isn't changing.
Right. If the state is steady, the properties are steady, right?
And they would be completely wrong.
Tell me why.
The source material makes a very specific, very sharp point about this. Even in a steady state rod that looks completely static to the naked eye, entropy is being actively produced.
Manufactured.
Yes, it is being generated constantly.
But how? If the state isn't changing, where is the entropy coming from? Usually we associate entropy with things physically getting messier or changing state.
Think about the reservoirs. You have a hot reservoir at a temperature we will call T1 and a cold reservoir at T2.
Okay, T1 is hot, T2 is cold.
Heat flows from hot to cold. That is just the second law of thermodynamics.
Okay.
Now follow the entropy.
Following it.
When a tiny packet of heat, let's call it dq, leaves the hot reservoir, that hot reservoir loses some entropy.
Right, because the definition of entropy change is heat divided by temperature. Change in S equals dq divided by T.
Exactly. So the hot side loses an amount of entropy equal to dq divided by a large number, T hot.
Because the temperature is high.
But here's the catch. The cold reservoir gains that exact same amount of heat energy. Energy is conserved.
Right, dq goes into the cold side.
But because its temperature is lower, the entropy it gains is actually larger.
Wait, run that by me again. Why is the entropy larger if the energy is the same?
Because of the denominator in the math, you are dividing the exact same amount of energy, dq, by a smaller number, T cold. When you divide by a smaller number, you get a bigger result.
Like the money analogy.
Exactly. If I give you $10, that $10 matters a lot more to you if you are completely broke than if you are a billionaire.
Right.
The cold reservoir values that heat much more in terms of entropy.
So the entropy gained by the cold side is mathematically larger than the entropy lost by the hot side.
Correct.
So the net result.
The net result is positive. The total entropy of the universe has increased. The time derivative of S, which we can call ds divided by dt, is strictly greater than 0.
That is the production.
Yes. The source text describes this as entropy production. Even though the rod looks entirely static, it is a factory generating entropy.
It is taking high-quality energy, hot heat, and degrading it into low-quality energy, cold heat.
And this production isn't just some philosophical footnote for textbooks. This production is the actual engine driving the hidden forces that are messing up the engineer's measurements right now.
He thinks he's looking at a still pond.
But he is standing in a current that is generating massive disorder.
That is a fantastic image. He is standing in a river of disorder. And that current doesn't just stay in its lane.
No, it does not.
Which brings us to part 2, the first glitch.
The glitch.
The engineer notices that the heat flow isn't just moving heat. It seems to be messing with his electrical readings and even the gas diffusion in that particulate filter.
This is where we have to introduce the core concept of coupling. This is the absolute heart of irreversible thermodynamics.
Usually in our undergraduate classes, we have these really nice separate laws.
Clean equations.
Right. We have Fourier's law, which says temperature difference drives heat flow. Simple. Then we turn the page.
To Ohm's law.
Exactly. Ohm's law, which says voltage difference drives current. Then maybe Fick's law a few chapters later, where concentration difference drives diffusion.
They stay in their separate chapters.
Right. They're polite neighbors who stay in their own yards.
But the source material points out that in the real world, in the messy, highly energetic world of engine testing, these forces interfere. They cross-couple.
Meaning heat can drive electricity.
And electricity can drive heat.
And heat can drive mass transfer.
And mass transfer can drive temperature changes. It is a massive interconnected web.
This sounds like absolute chaos for an engineer. If everything affects everything else, how do we even model that? How do you write an equation for everything is happening at once?
We use a brilliant framework developed by Lars Onsager. He was a theoretical physicist.
Okay, how does it work?
The source introduces a set of linear equations he developed. Basically, you have a flow, which we will call J, and it equals a coefficient, L, multiplied by a driving force, X.
Flow equals coefficient times force.
Yeah.
J equals L times X. That sounds simple enough. That is just like Ohm's law.
It starts out that way, but when you have coupled flows, it becomes a matrix of equations.
A matrix.
Let's say you have heat flow and electrical flow happening in the exact same wire. The equation for heat flow doesn't just depend on the temperature difference anymore.
It has a term for the voltage difference, too.
Yes.
So heat flow equals coefficient 1, so 1 times temperature difference plus...
Plus coefficient 1, 2 times the voltage difference.
That second term. With the coefficient L sub 1, 2, that is the cross-coupling term.
Exactly. It represents the interference. It tells you exactly how much the voltage is physically pushing the heat around.
And this is where Onsager won his Nobel Prize. So
Right.
It wasn't just for writing down a matrix. Anyone can write a matrix.
No, writing the matrix is just algebra. His Nobel Prize and the core insight of this entire source material is the discovery of the reciprocal relations.
Reciprocal relations, what does that mean?
He proved that the matrix is symmetric.
Meaning?
That means the cross-coupling coefficient L sub 1, 2 is exactly mathematically equal to the coefficient L sub 2, 1.
Pause on that. That sounds a bit abstract. What does that mean in plain English for our engineer in the lab?
It means nature has a deep fundamental symmetry. It means that the effect of temperature on electricity is mathematically identical to the effect of electricity on heat,
So if a temperature difference can cause a voltage,
which we call the Seebeck effect,
then an electric current must carry heat.
which you call the Peltier effect. You literally cannot have one without the other.
They're two sides of the same thermodynamic coin.
Exactly. You cannot design a sensor that uses the Seebeck effect without inviting the Peltier effect to the party. The math forbids it.
So why does this matter to the engineer right now? He is just trying to read a simple temperature on a screen.
Because it validates his confusion. He isn't crazy. He isn't imagining things. The physics of the universe demands that these things overlap.
Right.
If he has a temperature gradient on his test rig, he has electrical potential gradients happening whether he wants them there or not.
He is dealing with phantom voltages.
And phantom heat flows.
Which leads us directly to his biggest headache of the day. Part 3. Troubleshooting the thermocouple.
The bread and butter of thermal testing.
But evidently, it is vastly more complex than just twisting two dissimilar wires together and reading a dial.
It is the classic temperature problem in engineering.
So let's look at what the engineer is doing. He is using a standard thermocouple setup. He has his two wires. He has a voltmeter, which the source refers to as a potentiometer, to be precise.
Right.
And he's trying to measure the exhaust temperature.
Right.
But the reading is off. It is drifting around. It does not match his calibration data at all.
To understand why it is drifting, we really have to look at what a thermocouple actually measures.
Okay.
Most people think it measures temperature exactly at the tip where the wires meet.
It doesn't. I mean, I thought the little welded bead at the end was the sensor.
That is the most common misconception. The source material goes through a very rigorous derivation involving a concept called the entropy of transport.
Entropy of transport, they denote that as S star, right?
Yes, S star. And it is the absolute key to the whole mystery.
What is it?
The entropy of transport is basically the rate at which entropy is carried along by the flow of electrons.
Okay, imagine the electrons as little trucks on a highway.
Perfect analogy. They aren't just carrying electrical charge in their cargo beds. They are also carrying thermal energy and disorder.
Entropy.
Right. When electrons move from a hot zone to a cold zone, they drag this entropy with them down the wire.
So the electrons are multitasking.
Very much so. Now, looking at the sources analysis of the measurement circuit, we have wire X and wire Y.
Those are the two different metals of the thermocouple, say chromel and alumel.
Yes. Then we have the leads. Let's call them lead Z, which are usually just standard copper wires connecting back to the voltmeter.
Okay, the extension wires.
The total voltage that the meter actually reads is the sum of the potential changes across all of these wire segments combined.
And the source integrates this S star value across the temperature differences of each individual wire segment.
Correct. The mathematical derivation shows that the measured voltage depends entirely on the difference in S star between the two metals, integrated from the cold temperature to the hot temperature.
So it is an integral of the quantity S star for metal A minus S star for metal B with respect to temperature.
Yes, with respect to DT.
So far, so good.
Yeah.
That is how a thermocouple fundamentally works. The difference in how the two different metals carry entropy creates the voltage we read as a temperature.
Right.
So where is his error coming from? Why the drift?
The error comes from the connection.
The plugs.
Yes. The source highlights a very specific trap in the layout, often labeled as points C and E in the circuit diagram.
What are those points exactly?
These are the physical points where the thermocouple wires actually connect to the copper lids that go to the meter.
The junction between the specialized sensor wire and the cheap extension wire.
Exactly. Usually inside a plastic connector plug or on a screw terminal strip on the data acquisition board.
Okay, I picture that.
The golden rule, the absolute requirement derived directly from that S star integral, is that those two connection points must be at the exact same temperature.
Why? What happens if they aren't?
Because if they aren't at the same temperature, they act as a secondary parasitic thermocouple.
Ah.
Think about it. The leads are likely copper, material Z. If connection point C is sitting at 30 degrees Celsius and connection point E is at 35 degrees Celsius.
You have created a new thermocouple junction between the sensor wire and the copper.
Exactly. And that parasitic junction generates its own tiny voltage.
Which simply adds or subtracts from your main signal.
Right. The potential generated at point C doesn't cancel out the potential generated at point D because the temperatures aren't identical.
And the engineer mentioned earlier that his engine prototype is huge. It's a massive piece of metal. There are thermal gradients everywhere in that test lab.
Precisely. So picture his exact setup on the bench. He probably has his DAQ box sitting on a folding table near the engine.
Sure.
Maybe the tiny cooling fan from his laptop is blowing slightly on one side of the terminal block and not the other.
Or maybe one wire is just pulled a bit tighter and sits closer to the radiating heat of the engine block.
Exactly. That small, maybe 5-degree temperature difference across those two screw terminals is quietly injecting a rogue voltage into his measurement circuit.
So his quote-unquote hot junction reading on the screen is actually his hot junction voltage minus this parasitic junction voltage.
Yes. He thinks the engine exhaust temperature is drifting around, but actually, the room air temperature near his plastic connector is drifting.
That is maddening.
It happens all the time.
How does he fix it? Once he realizes this is irreversible thermodynamics at play, what is the practical fix?
The narrative fix is surprisingly simple once you understand the underlying thermodynamics. He needs to isothermalize those connections.
Isothermalize, meaning make them the same temperature.
Right. He needs to physically clamp the connection points together, electrically insulated from each other, obviously, so they don't short out.
But thermally coupled.
Yes, so they're forced to be at the exact same temperature.
Like sinking them into a solid block of metal.
Ideally, yes. An isothermal block A thick chunk of aluminum or copper that holds both screw terminals securely.
Because the metal block acts as a thermal bridge, balancing them out.
Exactly. That ensures that temperature T sub C perfectly equals temperature T sub E.
And once he does that, what happens to the math?
The potentials at those connection points perfectly cancel each other out because the integral from T sub C to T sub E is now an integral from, say, 30 degrees to 30 degrees.
Which is 0.
Exactly. And the reading on his screen immediately stabilizes. He is finally seeing the true temperature of the exhaust. The first ghost is gone.
Okay, so he fixes the drift. He is feeling a lot better. He takes a sip of his cold coffee.
Small victories.
But the engineer is thorough. He has been burned before, so he is paranoid now.
Good engineer.
He wants to check the physical resistance of his sensor wires just to be absolutely sure they aren't damaged or corroded from the heat.
Logical next step.
So he switches his multimeter over to the ohm setting and injects a small electrical current into the circuit to measure the resistance.
And that innocent action triggers the second glitch.
Part 4. The current and the heat.
Here we go.
As soon as he runs that tiny diagnostic current, the temperature profile of the wire physically changes. The steady state he just achieved is totally ruined.
This is where the cross-coupling we talked about earlier, those on-savior relations, hits him right in the face.
Why? What is he assuming will happen?
He assumes that running a current just creates standard resistance heating. You know, I squared R losses, Joule heating.
That is standard electrical theory. Wires get warm when current flows through them. Every engineer knows that intuitively.
But in irreversible thermodynamics, there is more going on. There is the Peltier effect.
We mentioned that briefly, the exact reciprocal of the Seebeck effect.
Yes. The source defines the Peltier coefficient in direct relation to the difference in the entropies of transport between the two metals.
So going back to S star.
Exactly. When an electrical current flows across the physical junction of metal X and metal Y, it doesn't just pass through seamlessly.
What does it do?
It must either absorb or release thermal heat to satisfy the fundamental entropy balance.
So unlike standard resistance heating, which always just heats up the wire regardless of which direction the current is flowing.
Peltier heating is fully reversible. It is directional.
Directional heat.
Yes. If the current flows one way, the junction heats up. If you reverse the battery and the current flows the other way, the junction actively cools down.
It acts like a tiny, solid-state refrigerator.
Exactly. It pumps heat.
So by simply checking the resistance with his meter, the engineer is actually turning the very tip of his sensor into a microscopic refrigerator or heater.
He is physically pumping heat into or out of the exact measurement point. He is wildly distorting the very physical property he is trying to measure.
He is changing the temperature of the probe tip just by asking it a question.
That is exactly what is happening.
That is incredible. But there is another effect at play here too, isn't there? One that is even more subtle than the Peltier effect.
Ah, yes. The Thomson effect.
The deep cut.
That is the deep cut of irreversible thermodynamics. The Peltier effect only happens at the distinct junction where two different metals meet.
Right.
But the Thomson effect happens along the entire continuous length of a single uniform wire.
Provided there is a temperature gradient.
Exactly. Not at a junction, but in the bulk wire itself.
Walk us through the mechanism of that.
Imagine the electrons flowing up the temperature gradient. They are moving from the cold end of the wire outside the engine up to the hot end attached to the exhaust.
Okay.
Think of those electrons like hikers climbing a very steep mountain.
I like this analogy. The electrons are the hikers. The temperature gradient is the physical mountain.
Right. Now, to climb that mountain, to move into the much hotter, highly energetic region of the metal, the hikers have to physically gain energy.
They need to match the higher thermal energy of the vibrating metal lattice around them as they go up.
Precisely. So where do they get that extra energy?
They have to take it from the mountain itself.
Exactly. They actively absorb heat from the wire lattice itself to fuel their thermal climb.
And by absorbing that heat...
They locally cool the wire down as they pass through.
Wow. And what if they flow downhill?
If the current reverses and they flow from hot to cold, they are descending the mountain.
So they have too much energy.
Right. They have excess thermal energy they need to shed in order to match the cooler, calmer surroundings at the bottom.
So they release heat into the wire.
Exactly. The source derives a mathematical calculation for this. The Thomson heat is strictly proportional to three things: the electrical current, the temperature gradient, and the specific Thomson coefficient of the material.
So let's look at the engineer's setup. He has a diagnostic current flowing through a sensor wire that runs from a 500-degree exhaust manifold out to a 20-degree room.
That is a massive thermal gradient.
Huge.
And as that meter current flows, it is actively redistributing heat all along the entire length of that wire.
It is physically warping the temperature profile of the metal.
It is not just heating up uniformly like a cheap toaster element. It is scooping up heat from one part of the wire and dumping it into another part.
The engineer suddenly realizes that by measuring the resistance, he is actively changing the state of the system.
This is effectively the Heisenberg uncertainty principle of macrothermodynamics. You literally cannot measure the system without disturbing it.
Especially if you use current.
Current is the disturber.
So what is his solution? How does he check his sensor or read the data without breaking the physics?
He must measure the voltage at zero current.
Zero current.
He needs a high-impedance voltmeter that draws virtually no electrons to take its reading.
The source heavily emphasizes that the pure Seebeck voltage is strictly a zero-current phenomenon.
Exactly. If J electrical, the flow of electrons, is not zero, you are immediately inducing Peltier and Thomson distortions on top of your signal.
So he cannot leave his meter on the resistance setting or use any DAQ channel that draws significant current.
No. He has to trust the purely passive voltage reading.
So he flips the switch back, he shuts off the current injection, he uses a high impedance channel.
And the drift vanishes.
The temperature readings are now rock solid. He wipes the sweat off his brow. He is feeling like a genius.
But the test is not over.
No, it is not. Because he still has those pressure sensors on the porous filter.
The filter.
Part 5, the third glitch. And this is the one that really freaks him out.
It would freak anyone out.
So he has this highly specialized ceramic filter sitting in the exhaust line. The engine is off now, but the heavy metal exhaust pipe is still incredibly hot.
It holds a lot of thermal mass.
Right. And there's absolutely no gas being pumped through the engine. The mass flow rate is identically zero.
Okay, zero flow.
But the pressure gauge mounted across that porous filter shows a distinct, measurable pressure difference building up.
A pressure head building up with absolutely no pump running.
He thinks it is a leak in the test cell or a fundamentally broken sensor. He is ready to tear the whole rig apart.
He is sitting there thinking, did I leave a bypass valve open somewhere? Is the sensor 0 point completely drifting out of spec?
But it isn't any of those things.
No, it is actually a really beautiful real-world demonstration of coupled diffusion.
Coupled diffusion.
Specifically, the deep coupling of mass transfer and heat transfer.
The source text talks about the Soret effect and the Dufour effect right around here.
Right. The Soret effect is when a strong temperature gradient causes a concentration gradient to form.
Like separating a mixed gas simply by heating one side of the container?
Exactly. And the Dufour effect is the exact reverse of that.
But in the specific context of the engineer's porous ceramic filter, we're looking at something the text calls thermal transpiration.
Also known as Knudsen flow.
Knudsen flow. That sounds like something straight out of aerospace or rocket science. What exactly is happening inside those tiny ceramic pores?
The source explains this phenomenon using a new concept called the heat of transport.
They label that as Q star, right?
Yes. Earlier we had S star for the entropy carried by electrons. Now we have Q star for the energy carried by physical gas molecules.
Okay. What makes this Knudsen flow behave differently from, say, normal airflow through a duct?
It entirely depends on the physical size of the holes in the filter.
The pores.
Right. Imagine the pores in this ceramic filter are incredibly small. Specifically, they must be smaller than what we call the mean free path of the gas molecules.
Mean free path. Explain that for us.
It is the average distance a molecule travels before it collides with another molecule.
Okay, so in a big, wide exhaust pipe, molecules are hitting each other constantly. Trillions of collisions?
Yes. They act like a fluid, but inside these microscopic pores, they barely ever hit each other. The pore is too narrow. They mostly just bounce off the physical ceramic walls.
So they're essentially flying solo through the tunnel.
Exactly. Now let's look at the temperatures. You have trapped hot gas on one side of the filter and cooler room temperature gas on the other side.
Because the engine block is still hot on one side.
The molecules on the hot side are moving much, much faster. That is what temperature is. They have higher kinetic energy.
Makes total sense.
But the source points out a fascinating statistical selection mechanism happening at the entrance to the pore.
A selection mechanism.
Yes. Because the hot molecules are moving faster and physically bouncing around much more often, the specific ones that actually manage to randomly hit the tiny hole and pass through to the other side carry a higher energy than the statistical average of the hot gas.
Oh, I see. They are the highly energetic outliers.
Right. They are the hot shots of the gas world.
So these hotshot molecules zoom right through the pore to the cold side.
They do. But here is the completely counterintuitive part.
Oh.
You would normally think the pressure would just perfectly equalize, right? High pressure pushes to low pressure until it's flat.
Always. That's Fluid Dynamics 101.
But because of this severe temperature difference and the specific way these solo molecules statistically hit the hole, you actually get a net flow of gas molecules from the cold side back over to the hot side.
Wait. From the cold, low-energy side pushing back to the hot side? That sounds completely backwards.
It does. It is called the fountain effect.
The fountain effect.
The severe temperature gradient literally forces gas mass to pile up on the hot side of the filter.
It is creating a pressure difference, a delta P.
Yes. Just to balance out the thermodynamic drive of the temperature difference, the delta T.
The source actually gives a specific mathematical equation for this, doesn't it?
It does, the Knudsen equation.
Right.
It rigorously relates the final pressure ratio across the filter to the square root of the temperature ratio.
So pressure 1 divided by pressure 2 equals the square root of temperature 1 divided by temperature 2.
Exactly.
So let's look at the engineer.
Yeah.
He is staring at a pressure gauge that reads a 1 psi of pressure, and he thinks there's a pump running or blockage. But actually the pressure is there simply because the ceramic filter is 200 degrees hotter on the engine side than on the tailpipe side.
The temperature gradient itself is physically creating the pressure head. The heat is doing the mechanical work of a pump.
That is just wild. It is like the heat is a physical wall pushing the gas backward.
It is. The engineer was frantically looking for a leak or a broken wire, but what he actually found was the heat of transport at work in the real world.
The gas molecules are just blindly obeying the fundamental laws of coupled flow.
They have no choice.
So how does he fix his data? He doesn't need to replace the expensive pressure sensor, right?
Not at all. The sensor is working perfectly. He just needs to account for the thermal transpiration effect in his data calibration.
No.
If his DAQ system knows the temperatures on both sides of the filter, which it does because he fixed his thermocouples earlier,
Right.
he can use the Knudsen equation to mathematically calculate the false thermally induced pressure head.
And then he just simply subtracts that calculated value from his raw sensor reading.
Exactly. He applies the thermodynamic correction factor, and suddenly his baseline pressure reads 0, exactly as it should with the engine off.
The engineer finally sits back in his chair. The mysterious temperature drift is entirely gone. The phantom pressure head is perfectly explained and corrected.
The prototype engine is actually performing perfectly within spec.
And he has officially mastered irreversible thermodynamics.
Well, he survived it, at least.
He didn't just fix a physical test rig. He finally understood the deep, invisible connections between these forces.
He realized that in the real engineering world, you literally cannot touch one variable without wiggling 3 others.
It is a really good feeling when the physics finally clicks.
Yeah.
We have essentially saved his million-dollar project.
All in a day's work.
But I know our listeners. They're engineers. They're detail-oriented.
They always have specific questions.
They want to know the edge cases. So let's move right into part 6. Frequently asked engineering questions.
Let's do it. I love these practical boots-on-the-ground queries.
Question 1. We talked about the physical wire length of the thermocouple earlier. Does the actual length of the thermocouple wires affect the accuracy of the reading?
Good question.
Like if the engineer has to run a massive 100-meter wire all the way from the test cell back to a remote control room, does that long distance degrade the thermal signal?
It is a very common worry. When you run long wires, you naturally worry about electrical resistance drops, you worry about picking up ambient noise, you worry about line capacitance.
Sure.
But strictly regarding the thermodynamics of the signal generation, the definitive answer is found right there in the S-star integral we discussed earlier.
The integral of S-star with respect to temperature.
Yes. The integral of S-star dt. Notice what specific variable is not anywhere in that mathematical equation.
Distance.
Exactly.
Yeah.
Distance. ddx, or length, is nowhere to be found. The total generated voltage depends entirely and only on the temperature difference between the physical endpoints.
So a 1-meter wire and a 1-kilometer wire will give the exact same millivolt output for the exact same temperature difference.
Theoretically, yes, 100%.
Yeah.
As long as the material of the wire is perfectly consistent, meaning it is metallurgically homogeneous throughout its entire length.
Okay.
You could tie the wire in physical knots. You could loop it around the outside of the building. It mathematically does not matter. The voltage is what we call a state function of the endpoint temperatures.
The path it takes doesn't matter. Only the start line and the finish line.
Exactly.
That is incredibly reassuring. Unless, of course, the wire isn't actually homogeneous.
Right. And that is the real-world catch. If the long wire has bad spots or kinks or severe rust, that physical damage changes the local S-star value of the metal.
And then the position of that damage in the temperature gradient suddenly does matter.
It matters a lot. But
Right.
assuming good quality wire, length is totally irrelevant to the core physics.
Perfect. Moving to question 2, cold junction compensation. We hear this specific term thrown around all the time in instrumentation manuals.
Constantly.
Why do we actually need it? Why can't the DAQ just measure the hot temp directly at the tip and be done with it?
Because of the deeply relative nature of the measurement itself. Look back at the circuit diagrams in the source text. You never actually measure a discrete temperature directly with a thermocouple.
You don't.
No. You only measure a voltage difference.
And that voltage difference is generated strictly by the physical difference in temperatures between the two ends.
Exactly. The thermocouple only tells your computer one thing. It says, the hot end out there is exactly 500 degrees hotter than the cold end right here.
Okay.
That relative difference is the only piece of information it gives you. If your computer does not know what the absolute temperature of the cold end is, that relative information is completely mathematically useless.
It is like me saying, hey, I am exactly 5 inches taller than Bob.
Right.
But if you have no idea how tall Bob is, you have no idea how tall I am.
That is the perfect analogy. The cold junction is Bob.
I like that.
Ideally, in a perfect lab setting, you physically plunge the cold junction wires into an actual ice bath at exactly 0 degrees Celsius.
Because then Bob is at 0. The math is easy.
Exactly. That is the physical reference we all agree on. But out in the field, like inside the engineer's plastic control panel, the quote-unquote cold junction is just the ambient air where the wires physically plug into the silicon chip.
Right.
So the smart chip has a tiny built-in thermistor that locally measures its own physical temperature, cold junction temp, and it mathematically adds that baseline back into the total reading.
Oh.
That specific math operation is cold junction compensation. Without it, your exhaust reading would falsely drift up and down every single time the room air conditioner cycled on and off.
Because the baseline is shifting. That makes total sense now. Okay, question 3. A listener asks, can I measure temperature with just one single metal wire? Why do I always need a pair of 2 different metals?
Good theoretical question. This loops right back to the entropy of transport concept.
S-star again.
Always S-star. If you have a single uniform wire, say just a pure copper wire, and you heat one end with a torch, electrons absolutely do physically flow.
There is a gradient. The hikers climb the mountain.
Yes. But if you actually try to measure that generated voltage, you have to attach 2 metallic voltmeter leads to the ends of the wire.
Which are themselves also made of?
Probably standard copper.
And if there are different metals?
You just accidentally built a thermocouple.
Right.
But if you use the exact same pure copper metal for the entire return path to the meter, the voltage generated by the hikers going on the way up the hot temperature gradient
Is exactly perfectly canceled out by the voltage generated by the hikers on the way back down the cooler return wire.
Precisely, because the inherent S-star property is identical for both paths. The thermal push up the wire is perfectly equal to the thermal pull down the wire.
So the total voltage integral simply loops right back to 0.
Every time. You physically need 2 completely different materials with 2 completely different S-star values so that the thermal push going one way is fundamentally stronger than the thermal push coming back.
And that tiny net difference is the actual millivolt signal your meter reads.
Exactly.
However, the source text does mention one very specific exception to this pair of metals rule.
It does, the Thomson effect.
Right.
You absolutely cannot measure the Seebeck effect of a single isolated metal, but you can physically measure the Thomson coefficient of one single solitary material.
Why?
Because that specific effect happens continuously along the bulk length of the wire itself, not exclusively at a physical junction between 2 things.
It is an intrinsic property.
It is the only thermoelectric property that is purely intrinsic to a single material. Measuring it is like measuring the specific like physical friction of the mountain path itself, rather than comparing two different mountains.
That is fascinating. All right, final question from the mailbag, and this one comes up literally whenever we start talking about the phrase production of entropy.
I can guess what it is.
It sounds highly suspicious to a lot of engineers. The question is this perpetual motion? Are we somehow getting free energy out of this steady-state system?
The answer is no.
Yeah.
Absolutely. Fundamentally, unequivocally no.
Good to be clear.
And the source text is very, very firm on this exact point. While these dynamic systems can settle into a mathematically stable, steady state, they are absolutely not free lunches.
Explain that simply. If the physical state is perfectly steady and unchanging, why does it continually cost us energy?
Remember what we said at the very beginning. Entropy is actively being produced. The term ds divided by dt is a strictly positive number.
Right.
That mathematically means the entire universe is continually becoming more and more permanently disordered because of your rod.
Okay.
To artificially maintain that steady state, to forcefully keep the metal rod hot at one end and freezing cold at the exact other end, you have to continuously pump fresh energy into the system.
You are paying a permanent energy tax.
Yes, you are physically burning expensive diesel fuel in the engine just to keep the hot side hot. You are running a massive electrical cooling fan to actively keep the cold side cold.
You are paying dearly in watts to maintain that steep gradient.
The continuous entropy production is basically the universe's thermodynamic bill coming due every single second.
Wow.
It is definitely not perpetual motion. It is the exact tragic opposite. It is continuous, unavoidable energy dissipation.
And the moment you stop paying that bill,
The moment you shut the roaring engine off,
the system immediately slides back down into a dead equilibrium, and all the magical thermal flows just stop.
the ghost vanishes.
Well, we have walked completely through the solid rod, the delicate thermocouple, the stray electrical current, and the mysterious porous filter. It really changes how you physically look at a simple benchtop test setup.
It absolutely does.
It is not just inert plumbing and dumb copper wiring. It is a highly dynamic, almost living system of interlocking flows.
We tend to get lazy and think of engineering as just static structural blocks, like this over here is a wire and this over here is a pipe, and they don't talk.
But irreversible thermodynamics violently reminds us that everything is continuously flowing and everything is deeply connected.
That is the whole point.
What is the absolute biggest takeaway for you personally from diving into this specific text?
For me, it is definitely the profound philosophical connection between the massive macro scale and the tiny micro scale.
That was so.
Well, we spent this entire deep dive talking about Lars-Onsager's relations, right? These big, clunky, macroscopic phenomenological laws where the massive matrix coefficient L sub 1,2 equals L sub 2,1.
Right. It is a very practical, wrench-turning engineering level tool.
It is. But the very end of the source material leaves us with a truly provocative thought in its final section on statistical mechanics.
Oh, right. The rigorous mathematical derivation.
Yes. Onsager did not just arbitrarily guess these symmetric matrix relations because they looked pretty. He rigorously derived them from the pure chaos of microscopic molecular motion.
He looked down at the atomic level.
He looked at exactly how trillions of microscopic particles randomly fluctuate and then slowly regress back to thermal equilibrium.
And what did he find?
He mathematically showed that the strict reversibility of time at the quantum atomic level,
The fact that individual bouncing atoms physically do not care which direction the arrow of time flows.
exactly, that microscopic time symmetry is the exact physical mechanism that creates the beautiful, predictable symmetry in the giant macroscopic engineering matrix.
So the totally random, chaotic bouncing of invisible atoms.
Actually strictly proves the rigid, practical laws of the engineer's thermocouple on the bench.
That is incredible.
The total chaos of the invisible micro one fundamentally creates the rock-solid, predictable order of our practical engineering world. It directly connects the invisible statistical behavior of billions of random atoms directly to the tiny red needle physically moving on the engineer's analog voltmeter.
That is a genuinely beautiful thought to end on. The terrifying ghost in the machine isn't some malicious poltergeist after all.
Yeah.
It is really just pure statistics.
Precisely. It is just countless trillions of atoms blindly trying to find their way back home to equilibrium.
Well, I think the engineer can finally power down his test cell, pack up his bench, and go home to get some much-needed sleep.
He earned it today.
And hopefully you, the listener, feel a little more equipped to tackle the thermodynamic ghosts haunting your own machines and test rigs.
Just remember the golden rule. Always physically check your junction temperatures.
Always check the junctions. Isothermal blocks save lives. If you haven't already, give us a like and follow, and please leave us a comment if you enjoy the podcast. We love to hear from the folks who make this possible.
Until next time.